Okay, so in this problem we have to derive a formula that will allow us to determine the value of an unknown resistor when we have three other resistors by balancing the voltage across this bridge known as a Wheatstone Bridge. So we have the supply voltage here, R1, R2, R3 and Rx. And we have points here A and B, and we have a potential difference between A and B over here, indicating that the higher potential is over here by A, lower potential here by B. So the first thing I think that we want to do, V equals IR. We know here that the current is going to split between these two paths. And they're going to be different. So we're going to have I over here, and we're going to have another I over here. Now we know that I equals V over R. Okay. We know the supply voltage is Vs. Now the path over here is going to display a resistance of R1 plus R2 because we've got resistors in series here. So we can say that the current over here that's going to actually split into this section here will be the Vs, V supply, over R1 plus R2. And we can say here that the current is going to split over here by Vs, it's the same voltage supply, over R3 plus Rx. R3 plus Rx. So we've got the current over here, again splitting on this arm, which will be Vs on R1 plus R2. And then we're going to have the current over here, which should be Vs on R3 plus Rx. All right? Just because, again, resistors in series. Now, what we need to do is determine the an equation for the or an expression for the electrostatic potential energy at A and B, and then by subtracting them, we're going to be able to derive the potential difference between A and B, hence the voltage on the bridge. So, let's see. So again, we know basically, again, basics V equals IR. Now, for A, we can say that V, voltage, is going to equal the current times the resistance, obviously. Right now, the thing is, here's the thing. When it goes through the first arm, we're not working out any potential difference here. We're just working out the electrostatic potential at one point, one theoretical point, relative to Vs. So, as the current flows through R1, we're going to get a power dissipation over here, i.e. we're going to lose, we're going to have certain amounts of energy per coulomb being transferred as heat. Now, V equals IR, so we can say over here that we know the current is going to be the same in R1 and R2. But again, we're just interested in what happens just after R1, so we can say that V equals IR, the I current is going to be Vs on R1 plus R2 times the resistance, which in this case is going to be R1. So we can say the voltage at A, or the electrostatic potential at A, will be Vs R1 on R1 plus R2. Now let's have a look at B. So VB, again, current is going to split. We've worked out that the current on the second path is going to be Vs on R3 plus Rx. VB equals IR. I current in this case will be Vs on R3 plus Rx times R3. Okay? Just because, again, once the current has passed through R3, we're going to get a voltage drop, and now the potential is going to be lower. So now we have expressions for the electrostatic potential at A and B. We also know from the diagram that the higher potential is going to be occurring at A here. So we can say that the actual PD AB or VAB, the actual potential difference between A and B will be VA minus VB, which simply is going to be VS on R1 plus R2 R1 minus VS on R3 plus RX R3. Okay? Now let's take the VS out of that. So we can say that VAB equals VS R1 on R1 plus R2 minus R3 on R3 plus Rx. Okay? So that's relatively straightforward. Now what we can do is rearrange this so that VAB will actually be equal to VS. That would be R1 R4 minus R3 R2 all on R1 plus R2 R3 plus R4. Now we can say that when the Wheatstone Bridge is balanced, i.e. VAB will be 0, at that point we're going to be able to we should actually be able to determine a value for Rx based on R1, R2 and R3. R2 here again being the variable resistor. Okay, so for this thing to be 0, the VAB, i.e. the bridge, to be balanced, we're going to set this to 0, so we can say that VAB equals 0, or when VAB equals 0, we can say that VS R1 R4 minus R3 R2 equals 0. Okay, because we only need the numerator to be 0. So from here we can see immediately that for the bridge to be 0, we can either have VS, the supply voltage, to be 0, or that's obvious and good, means we've some indication we've got the equation correct. And the other option is R1 R4 minus R3 R2 to be 0, i.e. R1 R4 equals R3 R2. Oh, I've just noted a little mistake. What I've done, I've just changed R4 to Rx inadvertently over here, but that's fine. We can just change that back again. We can set R4 equal to Rx. That's no problem. So now we can say that, I'll just rewrite that for clarification here. R1 Rx equals R3 R2. So what we can say is now, very simply, is that Rx on R3 equals R2 on R1.